So how does this all relate to derivatives? Well, already Sir Isaac Newton would have known that, or expressed this somehow in these terms. I've never read his writing, so I have actually no clue. But he would have said roughly that a derivative is a rate of change. It's a rate of change of something with respect to something. With respect to another quantity. And when we understand that that other quantity, the change of that is sent to zero. Now, this interpretation of the derivative is actually something you can generalize. You can always look, you have a quantity, and some other quantity changes a little bit. You can look at the ratio of the changes, and that should be some sort of a derivative. But in multi-dimensions, in higher dimensions, there are a couple of settings that you need to think about. So one simple setting, this is hardly needs really much to say, is that if you have, on the domain side, you have a function that takes in a real value and outputs something, outputs a vector. Well, such a function, if we wanted to look at its change, then this expression actually makes sense directly. So we say f is differentiable if the change of the function, this time the change is a vector, divided by h, that this converges. And we call this the derivative. Now, this convergence here is of vectors in Rn. And when does a vector or a sequence of points in Rn converge? We've proven in this class this happens if and only if component-wise converges. So if we write the components of this, so the components of f are f1 through fm, well then what we have here, if and only if each of the components has a derivative. So h goes to 0, f1 x plus h minus f1 h, x divided by h, dot, 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 of all the components. So, okay, if you have the domain as one variable, but the target has many variables, say prices of stocks in a portfolio that only depend on time, then you just differentiate each of them individually and put them in a vector. That's the change. In physics, that would be the velocity of them. So, and the components of the velocity are how fast each of the individual quantities change. Okay. So that's one setting. Well, the second setting that is really the interesting one that we will focus on is when the domain has many variables, Rn. Because when the domain has many variables, we have something like the temperature in space. The temperature depends on the location that you have, and it can change with respect to multiple things. So it can change with respect to x, with respect to y, and with respect to other directions. And that's the limits in these different directions that we were talking about. So there are different directions in this setting. And some context I won't really talk much about, and I won't ask since we only have 2 lectures, but you can say look at Rudin if you are very interested. You could have both depending on multiple things. You could have a quantity, say the velocity of wind or a wind field. It would depend on the position, so 3 coordinates. But it being a velocity field, every point would be associated with 3 things. So it would be a function from 3 variables, n equals 3, to m equals 3. That context is not very interesting the most interesting context for us is this middle one, and that will be already enough for us to analyze. And if you want to understand these other contexts, you can split the components, just like we did here. So kind of it's a combination of this plus this is equal to that if you just switch everything to components. Okay, so we're looking at rates of change, and we've honed in on this setting. So let's look at that setting, and let's look at a little bit of a picture relating to that. So we have a function, as I said earlier, that really weird interesting thing is already happens in 2 dimensions. So this is a graph of a function from R2 to R. And the crucial thing to have in your mind is that the function value here depends on 2 variables. It depends on as x changes or as y changes. That gives you 2 directions. But then there are all these other directions and all these other ways of converging along this graph. So let's see. And if we are sitting at this point, now, if we have a rate of change, well, one way of looking at the rate of change is that if we change the x component of the domain variable, well, changing the x component will change the function. But here you will get delta f divided by delta x. That will give you one slope. But another slope you will get if you change the y, and that will cause possibly another change in the function. This time you'd get the change in the function with respect to y. And these slopes don't have to have basically anything to do with each other. But in addition to these, you might be looking at a change in a third direction that is a combination of the other 2, and you could get a third slope in that direction, where you would have the change in the function times the length of the change in this direction, roughly speaking. So directional derivative in terms of calculus. And there doesn't have to be a relationship between any of these things. But it's still a rate of change, but just because we have multiple directions to go to, there are multiple ways of getting this rate of change. So that's the new thing that you get from multivariables, and that's why we have to think about how are we approaching. So derivative is then a rate of change with respect to something, either the x or the y or some third direction. Any questions so far? Okay. Well, this is all pretty hand-wavy, so let's try to make something rigorous, since this is a proof-based math class, and you'll have to actually prove things eventually. I mean, you can almost avoid this issue. So first thing was, what if we just change along the coordinate axes? What if we are moving just along, we have some point and we are moving just up or down or left or right or in higher dimensions along the axes in general? Well, we say that f from some omega to r, and omega is a subset of Rn, and it's open. It's usually open because we want to be able to move in all of these directions a little bit. So this function has partial derivatives at a point x, and we want to talk about this in n dimensions, so x1 through xn. Abbreviate that point as x bar. If the following limit exists, and this is just notations that we will use. So, well, what are we doing? We're looking at the rate of change. So how much does the function change? But only as we're moving along the ith direction. So the easiest way to write this is x plus, we go a little bit in one direction, t times ei, minus fx bar divided by t. If we write this in components without this vector notation, what does this look like? Well, we have, if we're ei is the ith basis vector, so it's only affecting the ith components. So we have x1, xi minus 1, xi plus t, xi plus 1, dot, 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 minus the original point, xn over t. So we're looking at what happens to the function as we increment the xith position from xi to xi plus t. And we're looking at the rate of change. There is an additional way of looking at this that I need to my laptop that so there's an additional way of looking at this is that we fix all the other components and we look at the function, a function of one variable. And this is the way that I would think most of the time, and this is the way that you should think in the homework, say, about this. So we can define a function, gi of t, which is just f x1, xi minus 1, and then we plug in t for the ith component. So this function becomes a function of one variable. And then this limit here is just the different of that variable, derivative of that variable. So fix x1, xi minus 1, xi plus 1 to xn, and then gi prime t is just partial I of f at x. Okay, so that gives us partial derivatives that we can define. Okay, well, now the second way of going is that we have our point. We don't restrict just going along the coordinate directions, but we go along other directions in direction of some v. So we define direction. We say that f has directional derivatives at a point x bar. And if you want to distinguish the direction, I'll just say for all directions. If for all vectors v in Rn, the following limit exists. So we're looking again at the change of the function, fx plus tv. So the change of the function, I want to make a size t step in the direction of v, and then divided by how big the time step is t. There's a little bit of a matter of convention whether you put the length of the vector v here in the denominator. I prefer not to do that. Most people, I think, would not do that. And there are some nice reasons why to do that. One is that way you can talk about the derivative with respect to 0. So if v is equal to 0, this term is just goes away. So you have fx minus fx equals 0. So that is always equal to 0. That's always defined. And with this convention, if you multiply a vector, then all you get is s times the derivative of f, as long as both sides exist, or as long as at least one of the sides exists. Okay. So that gives us directional derivatives. Now, already at this point, it's worth remarking, if v is equal to ei, the limit is the same as above. So we have that dei of f is actually just the partial derivative of f. So really, this is a general strengthening of the partial derivatives, where we talk about all directions, and the special cases of those directions are the coordinate directions that give us partial derivatives. Good. But, as said, these only control now the linear directions. So directional derivatives allow us to talk about if we're approaching along some line, either parallel to the axis or in some third direction, but it doesn't control sequences of points that curve to a point somehow. So the full derivative is the only one that controls all the directions in some uniform way. And its definition there is a little bit technical. So well, let's state it and then I'll highlight. So we say a function is differentiable at a point if there exists a linear function such that the change in the function minus this linear term goes to 0 as divided by h goes to 0. So a fake way of writing this is that fx plus h minus fx over h is equal to ax bar over ax bar h. Kind of if you put this on the other side. If you want to divide by h there. But this is not valid because you can't divide by a vector. So this doesn't quite make sense. So it's better to think of this just as a correction term here. But we will see a lot more what this does for you. But crucial thing here is this linearity. I'm going to focus on that. And then another thing is that this is a multi-dimensional limit. So this is the only definition out of the three that will control all the directions simultaneously. Okay.